All right, folks. Today we're going to explore recursion a little bit more by looking at some more sophisticated examples of recursion. So the first thing we're going to look at is the Fibonacci numbers sequence. And this is a really fascinating example of how a little bit of code that you can write can reveal the Fibonacci number sequence. And also I want to talk a little bit about what it means. So I've got a picture here that kind of demonstrates the idea behind the Fibonacci number sequence. And it illustrates something called the golden spiral. So let me explain how this works. So what we have here is a series of squares. So we'll get some purple, I think. Yeah, let's do some brightish pink. Okay, so here's how it works. The Fibonacci number sequence is a series of numbers that are built on previous numbers in the sequence. So the first number is 1. And so we're going to draw a square of size 1 right here. The second number in the sequence is also 1. So we're going to draw another square of size 1 right here. Now, we're going to build a third square based on the previous two squares. So the next number in the sequence, 2, is based on the sum of the previous two squares. So since the first square is 1, the second square in the sequence is 2, then the third square in the sequence is going to be 2. Sorry, the second square in the sequence is 1. So the first in the sequence is 1, second in the sequence is 1, add them together, we get 2. So we're going to build a 2 by 2 square. Now for the next square, we're going to base it, the next square on the sum of the next two numbers in the sequence, which are 2 and 1. So that's going to give us 3. All right, a 3 by 3 square. The next square in the sequence is going to be based on the two previous numbers, 3 and 2. And that's going to give us a square that's 5 by 5. And we continue that. 5 plus 3 gives us 8. 8 plus 5 gives us 13. 13 plus 8 gives us 21. All right. Now, if you build squares in that pattern, and then you connect the squares using a slight arc going from, I'll give you an example, a slight arc going from one corner to another corner, what you end up creating is a spiral that's called the golden spiral. Now, the reason why this spiral is so fascinating is, well, first of all, it's a construct based on Fibonacci numbers, which is interesting. But secondly, it shows up in nature over and over and over again. So here is an example of the nautilus shell. And the spiral in a nautilus shell is really a golden spiral built up out of these squares that are based on the Fibonacci number sequence. Really fascinating. And it turns out that there are many things in nature, including the spirals that you see in the seeds in a sunflower, or the spirals that you find when you look carefully at cones, pine cones. In fact, not only do the spirals themselves follow the golden spiral sequence, but if you actually count the number of spirals that you find in a cone, for example, you will see that the number of spirals going in one direction and the number of spirals going in the other direction in something like a pine cone is actually a number in the Fibonacci number sequence. So that's really interesting. Now, of course, we can't do really cool graphical things to display this golden spiral right now, although really, if you take CS104 next semester, you would be able to do something cool like that. But what we can do is we can just talk about the numbers in the Fibonacci number sequence. It doesn't really matter where we start, but why don't we do this? Let's start at 0. All right, so 0 is the first number in the Fibonacci number sequence. 1 is the second number. 1, now we say 0 plus 1, and that's going to give us the third number. So in effect, well, let's just do that. So this is the third number. Now we add 1 plus 1. We add those together to get the next number. That's going to be 2. Then we add 1 plus 2 together, and that's going to give us the next number. That's 3. 2 plus 3 is, oh, we'll say let's do this. So let's see. I'm going to just turn off notifications. We don't really need to be seeing text messages right now. Ugh. Okay. All right. Let's go back to here. All right, so this is the fourth number in the sequence. This is the fifth number in the sequence. And 3 plus 2 gives us 5. 3 plus 5 gives us 8. 8 plus 5 gives us 13. 13 plus 8 gives us 21. 21 plus 13 gives us 34, and maybe we'll stop at the next one. 34 plus 21 gives us 55. Okay, and we can continue on for a while. All right, so the observation here is that each sum, or each number in the sequence is the sum of the previous two numbers in the sequence. That's the observation we're going to have about the Fibonacci numbers. So every number in the sequence is a sum of the previous two numbers in the sequence. Okay, so if that's true, and we want to be thinking about things recursively, oh, we have an exception, and that is except the first two numbers, right? Except for 0 and 1. They are just magical. They're the first two numbers in the sequence. We just say the first two numbers are 0 and 1. Okay. So let's say that we wanted to write a program that worked like this. The program was, we wanted to find a method called fib, oops. We wanted to find a method called fibn. And what this does is it returns the nth Fibonacci all right. So if we said fibn of 5, it's going to return the number 3. If we said fibn of 6, it's going to return the number 5, and so on. If we said fibn of 1, it would return the number 0. So that's the idea of fib, all right? So we want to define this recursively, and it turns out if you define it recursively, the amount of code that you have to write is actually fairly trivial, all right? So we're going to say that n must be greater than or equal to 0. Oh, sorry, greater than or equal to 1. All right, because we're starting out with the first number in the sequence is the value 0. Okay, and so to define this, what we should do, first of all, we have to recognize that there's definitely some recursion going on here. If we're saying that each number in the sequence is based on the previous two numbers, then we're defining this method in terms of simpler versions of the method. So this is a recursive definition. All right, so fib of n is equal to, basically, let's think about it. So the Fibonacci number, the fifth Fibonacci number, is based on the sum of the fourth Fibonacci number and the third Fibonacci number, right? So maybe we can just write that down. Fib of n is based on the previous Fibonacci number plus the previous Fibonacci number. Now this is definitely a recursive definition. Cool. So this is going to work itself backwards, finding Fibonacci numbers that are earlier and earlier in the sequence until we hit a base case, right? If we don't define anything else here other than this definition as it stands, we are going to have infinite recursion because n will keep getting small. N minus 1 will get smaller and smaller. Every time we try to find Fibonacci of n, we're going to get Fibonacci of n minus 1 and n minus 2, but each one of those has to be resolved, which are further Fibonacci numbers going further back. And if we don't stop at some point, we'll just keep going back and doing negative numbers for Fibonacci numbers, and it's just going to be a big mess. So we really have to stop the recursion. This is our recursive case. So we have to come up with a base case. Base cases are cases that stop the recursion. So they return a value. So they don't return another invocation of a simpler version of the method. So if n is equal to 1, then Fibonacci of n is equal to 0. Else, if n is equal to 2, then Fibonacci of n is equal to 1. Awesome. So these are base cases right here that stop the recursion. Else, we're going to do this recursive case. So that's kind of a rough sketch of how we want to attack this problem. And let's just take a look at that, see how that works as we move back. All right, so the fifth Fibonacci number is based on the sum of the third and the fourth Fibonacci numbers. Well, if we want to resolve what those two Fibonacci numbers are, the third and the fourth, we want to figure out what those are, and we don't know them yet, we're going to go back further. And so the third Fibonacci number, as an example, is the sum of the second and the first Fibonacci numbers. Now, the second and the first Fibonacci numbers, those are already resolved. Those are base cases. So the first Fibonacci number we know is 0, the second Fibonacci number we know is 1, and that's because we wrote these base cases right here that say if n is 1, then Fibonacci of n is 0, and if n is 2, then Fibonacci of n is 1. So since these two Fibonacci numbers are resolved in base cases, we can quickly compute our third Fibonacci number. And we say that that's 1. So that's an example of how the base cases and recursive cases work together. So we're going to work out a more complex example of a Fibonacci number getting resolved in a moment, but I thought it would be useful to maybe switch over to writing some code now that actually puts this together in some Java code, and then we'll run it, we'll look at the results that we get, and then we'll actually do a trace of this so we can understand the Fibonacci numbers and the recursive solution to them a little bit better. Okay, so let's write some code in Codio. Ouch, that was loud. And we'll call this program Fibonacci. Let's try that again. Fibbonacci. Okay. And we'll just grab a little code from, just to start from summation to get it working. Okay. And this is going to be called Fibbonacci. Need a little bit more help here. Let's find the main program. Okay. Now, what we'd like to be able to do, if I'm thinking about the main program, is I would like to do something like this. System.out.println, enter n. All right, so we'll have the user enter n, which is to find this, let's say, n, to find an number in Fibonacci. Sequence. All right, so then we're going to get an n, so int n equals input.nextInt. We're going to need a scanner to make this work. So let's grab our, actually I'll just create the scanner just before I need it. So scanner input equals new scanner system.in. All right, so we have our scanner, we have our n, and then we're going to say system.out.println the nth number in Fibonacci sequence is, and we're going to call the Fibonacci method. We'll spell it out. N. There we go. Cool. All right. So when we run this program, it's going to say, give me an n to find the nth number in the Fibonacci sequence. And then we are going to grab an n from the user, and then we're going to call the Fibonacci method that we're about to write and ask what is the nth number in the Fibonacci number sequence. Okay. So if we put in the value of 6 as our value for n, we'll get the value of 5 back. If we put the value of 7 in, we'll get the value of 8. If we put the value of 8 in, we'll get the value of 13, and so on and so forth. All right. Now, the code that we're going to write to make this work is based on the work that we just did here. If n is 1, we're going to have that Fibonacci method return 0. If n is 2, we're going to have the Fibonacci method return 1. And anything else, we're going to have the Fibonacci method call itself recursively to resolve what its value is. All right? So there's not that much code to write here. All right, let's write the code. Int public static int Fibonacci int n. All right. So I'm going to just have it return 21 for a moment, just because I want to show you again the awesome power of stubs. So the Fibonacci method doesn't do anything just yet, but it does let me run the program and kind of test out the main program. And remember, the main program always acts as kind of an outline for what it is that we want to do. So I'm just demonstrating good stub programming. All right. Oh, that's weird. Huh. Interesting. Oh, right. So one thing that I'm doing that you might be noticing in the videos is there's a lot of code that we've been writing in class. And to organize the code, I put the code into folders, right? So based on the kind of section of the course, I wonder if I can even organize the file. I don't think I can. Maybe. That would be cool. No, I don't want to do that. Oh, phooey. Can I get that back? No. Okay, let's just move this out here. There. And the folders are organized alphabetically. All right, so we're currently working on Recursion. And so under Recursion, we have a bunch of programs. But if you just click on the program that you're trying to compile, and you click compile and run, if the program's in a folder, it will say there's an error. So you have to tell the terminal window where the folder is. So I'm going to go into the Recursion directory, press enter, and now I'm in the Recursion directory, and now if I say compile and run, it'll find the program. All right, so enter n to find the nth number in the Fibonacci sequence. All right, we're going to enter the number 4. And it says the nth number in the sequence is 21. Okay, no matter what I do when I run this, if I put in 9, it's always going to say that the nth number in the Fibonacci sequence is 21, and that's because we haven't written the actual code to make the Fibonacci method work yet. But we were able to test out the main program, so we know that it's behaving pretty much the way we want it to behave. All right, so let's go and write the code. Now the code that we're going to write for Fibonacci is based on the code here, and it says if n is equal to 1, then Fibonacci of n should return 0. Well, that sounds like an if statement, so let's write that. So if n is equal to 1, then Fibonacci of n should return 0. All right? And the next thing is if n is equal to 2, then Fibonacci of n should return 1. Else, if n is equal to 2, then we're going to return 1. Else, Fibonacci of n is equal to the recursive case, Fibonacci of n minus 1 plus Fibonacci of n minus 2. So that means else we're going to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. And that's it. Now you might be saying, what? How is that possible that all of this complexity and beauty that we just talked about here, starting with this computation of squares and creating arcs between the squares and looking at it in nature, and then talking about this sequence, ends up being just a few lines of code? And what I'll say is that that is one thing that's really beautiful about recursive solutions to problems. Often it is just a few lines of code, but it's a little bit like a haiku where you have just a very tight, you say in a few words something that's very meaningful, okay? And so that's what's happening here in recursion. That's not always the case. You can have recursive methods that are very complex, but often the solution, if you think about it and work through it, will end up being something that's very, um, very succinct. And that's why recursive solutions to problems are often preferable to solutions that use while loops or for loops, or what we would call iterative solutions. Okay, so we've got the whole thing written here. Let's give it a test run. All right, enter n, find the nth number in the Fibonacci sequence. Let's just test it by looking at a number. So if we enter an n of 6, we should get the number 5. All right, so 6. Yep, the nth number in the sequence is 5. Okay, let's enter another one. Let's do the number 7. We should get 8, which we did. And we'll do 9. So if we do 9, this is 7, 8, 9, we should get 21. Perfect, 21. All right, so it looks like our Fibonacci number sequence program is working. But I think it would be worthwhile to trace the behavior of this with a number in the sequence, or an n, which returns a number in the sequence. So what I thought it would be worthwhile doing is, maybe what we could do is, I'll rewrite the sequence up here. I'll rewrite the sequence here. So 0, 1, 2, whoops, 0, 1, 1, 2, 3, 5, 8, 13, 21. And I'm just going to mark what number in the sequence this is as well. So this is the first, second, third, fourth, fifth, sixth, seventh, eighth, and ninth. Okay. All right, so what I want to do is let's trace Fibonacci of 5. I'm just going to abbreviate it as fib of 5. So we make an initial call to our Fibonacci method. I didn't spell the whole thing out, I just abbreviated it as fib. So we make an initial call to Fibonacci of 5. Now, if you look at the code here, the code says if we come in here with a number of 5, n is not equal to 1, and is not equal to 2. So the Fibonacci of 5 is going to be resolved by figuring out what the Fibonacci of 4 is. And adding to that the Fibonacci value of 3. Okay, so that's the breakdown of Fibonacci of 5. Now, in order to actually return a value for Fibonacci of 5, though, we have to resolve the Fibonacci values for 4 and Fibonacci value for n equals 3, the third number in the Fibonacci sequence. So that process is not immediate because we don't actually know what the value for Fib4 is or Fib3, so we have to resolve that through recursion. So the Fibonacci value for 4 is the Fibonacci value for 3 plus the Fibonacci value for 2. And we have to resolve Fibonacci of 4 first because it is the first part of the expression that computes the Fibonacci value for 5. So we're going to do Fibonacci value for 4 first. So since we don't know what Fibonacci value of 3 is immediately, there's no base case for that, we have to resolve that as well. So Fibonacci value for 3 is the Fibonacci value of 2 plus the Fibonacci value of 1. Okay, now things get more interesting and we can start resolving some values. because the Fibonacci value for 2, we do know what that is. If you look here at the code, you can see that if n is equal to 2, Fibonacci of 2, we're going to return the value of 1. So we're going to stop the recursion and return the value of 1. So Fibonacci value of 2, that returns the value of 1. And we also, when that is returned, to this expression for fib2, we now effectively have 1 plus whatever the Fibonacci value of 1 is. So that 1 is returned here to the call to Fibonacci of 2. So now we have a 1 plus Fibonacci of 1. Well, Fibonacci of 1 is also a base case. The Fibonacci of 1 is 0. All right, so this resolves to 0. This 0 is returned back here as the value of Fibonacci of 1. And so when you have 1 plus 0. Now, this expression can be added together, 1 plus 0, that's 1. And that can then be returned to Fibonacci of 3. And so this has the value of 1. And we can add to that Fibonacci of 2 here. And Fibonacci of 2 is a base case. You know that base case resolves to the value of 1. So now we have 1 plus 1 for the expression of Fibonacci of 4. And 1 plus 1 evaluates to 2. So that value 2 is then returned to Fibonacci of 4. Wow, there is a lot that's going on here in order to resolve Fibonacci of 5. Now, we haven't even resolved it all yet. We still have to figure out what's going on with Fibonacci of 3 here. But at least we now know that the Fibonacci of 2, or Fibonacci of 4, resolved to the value of 2. And we can just check that, right? Look up here. The fourth value in the Fibonacci sequence is the value of 2. But we can see how this can be resolved recursively instead of just looking up in the table. All right, so Fibonacci of 3 is a little bit repetitive, but I think it's worthwhile. So the Fibonacci of 3 resolves into a recursive expression of the Fibonacci of 2 plus the Fibonacci of 1. Now, we don't know immediately what Fibonacci of 2 is, but when we make the method called the Fibonacci of 2, that resolves to triggering a base case which returns 1. That 1 is returned to Fibonacci of 2, and so now we have an expression which is 1 plus, we don't know yet. We have to figure that out. We have to figure out what Fibonacci of 1 is. Well, Fibonacci of 1 also triggers a base case and returns 0. So it's 1 plus 0. And when we add those two together, we get 1. And so the value of 1 is returned. And that is what Fibonacci of 3 gets resolved to. And so now, finally, we can figure out what Fibonacci of 5 is. Fibonacci of 4, through a bunch of recursive calls and then finally triggering base cases, return the value of 2. Fibonacci of 3, through a recursive call and then quickly triggering some base cases, resolve to the value of 1. So now 2 plus 1 is going to give us 3. And so the value of this expression, 2 plus 1, is now returned from Fibonacci of 5, and we'll have the value of 3. And if we look, the fifth location, the fifth n, does have the value of 3 in the Fibonacci number sequence.